So for today's lesson, we're going to continue on with physics, and we're going to talk a little bit about how light travels, as well as how light interacts with different surfaces. So when I'm talking about light, I'm not only talking about the little bit of light that we typically think about, like light bulbs or the sun, but I'm talking about the entire electromagnetic spectrum. We actually classify all of this as light because it's not a different type of wave, it's just a different type or distance in the wavelength. So when we're talking about radio waves, that's a longer wavelength versus gamma rays are very, very tiny distances between the wavelength. So when we're talking about radio waves, that distance between the waves is about the size of a building, so quite large. And when we get all the way to gamma rays, which can be quite dangerous, the distance between the wavelength is about the size of an atom, so quite a bit smaller. So all of this exists along a spectrum. So when I say the word spectrum, I mean kind of a continuum, so something that continues along the same path and just kind of changes. So you might have heard of the autistic spectrum. So someone with autism could have very, very profound autism versus kind of a lower form of autism and have kind of less challenges that they have to deal with. So this is kind of what we're talking about when we're talking about light. So this whole thing is sitting along a spectrum. So it's not a different thing, it's just a different distance between each of these waves. And what we're going to focus on for the rest of our unit is we're talking about this very, 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 very small corner that we know as the visible spectrum. This is what you can see and what you interact with most on a day-to-day kind of life. So just kind of basic kind of review of the electromagnetic spectrum. It's invisible as it travels. You can't see waves traveling. It's involving the transfer of energy from one place to another. So energy is traveling in the wave. And it can travel through empty space. You may have heard about the speed of light before. The speed of light is incredibly fast. It can go around the Earth. So light can travel around the Earth 7.5 times in 1 second. So that gives you an idea of just how fast light travels. I'll show you a little simulation that I have to show you the speed of light. So that's light traveling around the Earth 7.5 times per second. This is how fast it would take light to travel to the moon. So it can travel quite fast. This shows you kind of the distance between Earth and Mars. So this light traveling from Earth is going to take about 3 minutes to get to Mars. Light traveling from the sun is going to take about 8 minutes and 17 seconds to get to Earth. So when you think about the speed of light, that should kind of help. So it moves very, very, very fast. Visible light we use as a model to study all of the other kind of parts of the electromagnetic spectrum because it's safe and easy to study. So lots of these models that we're going to discuss today work with kind of different sectors of the electromagnetic spectrum, but we're going to focus on light, visible light specifically, because it's the safest and easiest to study. So it's not going to cause cancer or very harmful radiation. So the visible light spectrum is the section of the electromagnetic spectrum that is visible to the human eye. So it's the part that I can see. We're talking about sunlight. This is the reason you can see color and light from light bulbs. As I mentioned before, the visible light spectrum is made up of more than just white light. So when you're switching on your light bulb or standing in the sun, what you can't see is that white light is actually made up of all of these different color wavelengths. We just don't see them because when they're traveling together, they appear white. So Isaac Newton, the man who discovered gravity, also discovered that white light is a mixture of colors. This was his discovery. How he did this is he used a prism, so a glass kind of triangular object, to separate the visible light into colors. So when the light traveled into this new glass prism, what happens is the light actually bent, making all of this visible. Why did it do this? So the white light that came and traveled was made up of all of these different color wavelengths. So when we think of light, white light specifically, it also exists along a spectrum. So red is at a longer wavelength, so right next to red on the other side of this, so this is where the visible light spectrum begins, so it encompasses all those colors. On the other side of this, we've got infrared rays. On the other side of this, we've got ultraviolet. So all of those colors are a continuation of the spectrum. So at the beginning, we get longer wavelengths, just like infrared, radio waves. And as we go closer to ultraviolet, gamma rays, and X-rays, our wavelength gets shorter. So there's all different types of wavelengths here. So when light travels through another material, so when it travels through this glass, also when it travels through water, any type of different change in material, what happens is the light is going to refract, which is a word for bend. So it refracts or it bends. Long wavelengths like red are going to bend less. So you can see that it's kind of coming off at a different angle. So it's not coming out as much of an angle as this violet is here. Versus shorter wavelengths like violet are going to bend considerably more. So if I kind of grab my pen, I can give you a little bit more of an idea. So if light was traveling just straight through the medium, it would end up around here. Obviously, it's not doing that, so it's bending a little bit. So the red light is coming off at this angle, maybe even a little bit more than that, versus the violet is coming off more around this angle. So it's kind of angling out quite a bit more. So when all of these colors get an opportunity to spread out because they have different wavelengths, that allows you to see all of those different colors. And we'll talk a little bit more about refraction later and how it kind of relates to how you see rainbows and all of that other stuff. But what is important to kind of understand today is that this white light, so the light that's coming from your light bulb, from the sun, is made up of all of those different wavelengths. It's not just white light, it's a combination of these different colors. You just can't see the difference between them unless it's being refracted. Okay, so when light hits an object, a shadow is created behind it. Have you ever thought about how come? So light hitting this object, why doesn't the light show up here? And why is the shadow being created? So things that shadows show us, and they inform us a little bit of kind of information about light, is that light cannot travel through opaque objects. When I use the word opaque, I'm referring to something that can't be seen through. So it's a solid thing that you cannot see through, like a piece of wood or a book. Light travels in straight lines that we call rays. So these things here with the arrows are called rays. This is how we diagram light. And when an opaque object stops a light ray from continuing its path, a shadow is formed. So when light travels, it hits an opaque object. It can't just go through the opaque object. What happens behind it is there's no light traveling and a shadow is created. So like an absence of light. So ray diagrams, these diagrams can be used to study and predict how light behaves when it reflects. So when light bounces off a surface, when it bends, refracts, as we were talking about with the different color wavelengths in the prism, when it transmits, and when it absorbs. So our goal for today is not to kind of go through all of the information about reflection, refraction, transmission, and absorption, but for me to kind of introduce you to each of these terms so we can spend more time looking at some of these other things in relation to how eyeglasses work and how different types of mirrors work. Oh, and before we kind of run off, I want you to remember that even though we're drawing light as a ray now, so as a straight line, light is not traveling just in rays. It's kind of a more simplified view of light traveling in a wave. So if I had to diagram all of these different wavelengths, my diagrams would get quite messy. They'd probably become quite confusing, and I'd have to do them very precisely to understand kind of what was going on. So what scientists have done instead of drawing all of these waves is they've created a simplified version of it kind of coming off in a ray. But really what's happening, so yeah, I can't even draw it precisely enough, is we've got waves traveling in these rays. Okay, so when light interacts with a surface, it can do one of three things. It can be reflected, so it bounces off of that surface, so it hits something like a mirror or a really shiny object and it bounces right off. It can be absorbed, so if you think of something that's black, anything that's black is absorbing light, so the light is being sucked into the object in the form of heat, so black objects will get hot. Or it's being transmitted, so it's traveling through. So something like a glass or a window that's having light being sent through it. So reflection is the process in which light bounces off a surface and then changes direction. So it comes at a surface and then it's going to bounce right off. Light can reflect not only off of smooth surfaces like mirrors or like really, really smooth glossy things of water, but it can also reflect off things that are less smooth or rougher, ranging all the way from a lake that's got a little bit of waves coming off of it, it's still reflecting light, or something as rough as a piece of paper or any type of object. So it reflects off rough surfaces like paper, and this is what allows you to see the object. And we'll talk a little bit about the difference between this smooth, glossy type of reflection and a kind of rougher reflection. So reflection in smooth and rough surfaces. We can see objects because light is being reflected off of them, or they are a light source. So obviously you can see a light bulb because it's glowing, or the sun because it's glowing. So light sources are kind of visible because they're emitting light. Other objects that you can see, some light is being reflected off them. There's kind of two different types of surfaces reflecting light. So reflection of a light can be specular, mirror-like or glossy. So when you're thinking about light coming in a mirror or reflecting off a very smooth body of water, what's happening is light is coming in, and because the surface is so smooth and it's not got any bumps in it, it's just going to bounce right back off. And it's going to actually bounce, if we measured the distance here and the distance here, we'd actually be coming in at the same angle. So these angles would be equal. And this kind of smoothness is allowing me to see the image being reflected back in the object. So it needs to come in at a very, very straight angle, and the surface needs to be quite smooth. The Earth's ocean has a specular reflection, but also objects that are really, really shiny metal or very, very smooth glass can also cause this type of reflection. Another type of reflection, the one that you probably don't typically think of as reflection, is diffuse reflection. So what happens when a surface is really, really bumpy? So you can't really tell when you're looking at a piece of paper, but a piece of paper isn't just flat and smooth. It's actually got lots of little grooves and kind of marks in its kind of texture that cause this type of reflection. So scattering occurs. So what happens is the light comes in, but instead of bouncing back at a nice angle that allows you to see a reflection on the other side, what's happening is the light's kind of going off in lots of different directions. So it scatters and it sends light off in many different angles. So what this does is it creates kind of not an illusion of like super glossy or mirror, like it doesn't reflect the image back in it, but it's still reflecting because that's what's allowing you to see it. So the lunar surface is an example of this type of reflection, as well as this kind of ball. And most objects that you're interacting with and seeing in your everyday life are going to be diffuse. Things like mirrors or metal are going to fit into this type of reflection. Absorption is the process in which light waves are trapped in an object as heat. So when light comes in from like a light source, so we can talk about the sun, it's coming in as white light. So white light travels. We know that white light is actually composed of all of these different color wavelengths, even if we can't see it. And what happens when it interacts with the surface that we see as black is all of these colors are actually being absorbed. So they're not bouncing back off into your eyes, and you're gonna see this as black. So when we see the color black, it's because no colors from this spectrum are being reflected. This is also why wearing black in the sun makes you hot, because all of these waves that are coming in, light waves that are coming in, are actually being trapped in this surface as heat. So that's when if you get into a black car or you're wearing a black t-shirt out in the sun, that's why it's going to feel extremely hot, because all of that heat energy being transferred here is going to stay in this object because none of it's being reflected out. So this is how we see color, because some colors are being reflected and some are being absorbed. So when white light hits an object, so again, white light is coming from the sun, we don't see all the colors, we just perceive it as white light. Some colors are being absorbed in the surface versus others are being reflected. So the reflected colors are actually what we see. So a leaf absorbs red, orange, yellow, blue, violet, and indigo. So all of these colors are staying in the leaf, they're being absorbed, and the leaf is going to reflect the color green back into your eyes. So this has to do with the texture or surface of the leaf, its chemical properties that tell it kind of what color it's going to be, and this is your perception or view of what the color is. So I'm seeing green when I look at this leaf because all of these other colors are being absorbed. When we're looking at something that we see as white, what's happening there is that white light is again coming in from something like the sun or a light bulb. It's coming in as white. We can't see these colors. And then it's bouncing off a surface that is white. And all of these colors are actually being reflected. So again, we perceive all of these colors as the color white. And this is also why wearing white in the sun makes you less hot. So white is being reflected back. None of this heat energy is being trapped because all of these colors are being bounced right back off. So that's why you don't get as hot when you're wearing a white t-shirt. Transmission. Transmission is the process in which light passes through a material. So light's traveling through something like this window. You see it on the other side. Different materials transmit different amounts of light. If I held up this white paper against a light bulb, I would get some light traveling through it, probably not as much as I would for this window. So clear glass windows transmit more light than a sheet of paper. What can light travel through? So you can see here a little bit of this thing that my teapot over here is a lot more visible than my teapot over here. It's because these materials are classified differently, and we're going to talk a little bit about that. So you might have already talked about this, so I'm going to kind of quiz you on it. What types of material can light travel or be transmitted through? So will light transmit a translucent through a translucent material, a transparent material, and an opaque material? So if a material is transparent, so we're talking like a window or a glass, all light is going to pass through. It's something that you can see through, look through. We're talking about sunglasses, otherwise you'd hit objects, glasses, windows, all of those sorts of things. A translucent material, only some of the light is passing through. We're talking about something like wax paper or paper. So it's not something you can see all of the information through, but it's letting some of the light go through. An opaque material lets absolutely no light go through. We're talking about something made out of wood or stone, so no light is traveling through it. Classifying these materials is pretty straightforward, so we're going to go over a couple ways to do that. So materials can be transparent, translucent, or opaque, depending on how much light passes through. So if lots of light goes through versus a little bit of light versus absolutely no light. How light behaves when it interacts with the surface, so if it fully transmits versus reflects or absorbs, and if you can see through it. So little review. Transparent materials transmit almost all light rays, so they all travel through, they make it to the other side. Objects can be clearly seen through them. We're talking about a window. You can see what's going on the other side of a window. or a plastic Ziploc bag, or a glass of water. So you can see through that object. Or glasses would be another great example. Examples include clear glass, plastic, air, water. So light's going directly through, traveling, doesn't change angles. It's all going well. Opaque materials are going to either reflect, so you can see that here, so it's bouncing off, or absorb light. So it's either going to bounce off if it's a really smooth, shiny surface, or it's going to absorb light if it's something like a black object. It does not allow any light to pass through. So there's absolutely no light on this side. If something is opaque, it doesn't transmit light. Objects cannot be seen through them, so I can't hold up a book and see through it. Examples could be wood, metal, stone, etc. So no light passes through. It's either being absorbed, like we discussed, or bounced off, reflected. Translucent materials scatter light. So what happens when a translucent material has light hit it is some of the light's going to travel through, some of the angles might kind of bend and go a little bit wonky, some of the light's going to bounce right off, so some of it's being reflected, and some of it's being absorbed. So translucent materials allow most light to go through. So most light is traveling through, but the light is being scattered in many different directions as it passes through, which makes your vision of whatever's on the other side of it really difficult. So you can't see the exact details. Objects seen through them are blurry. Examples include frosted plastic or wax paper. So it's something you can see through somewhat, but not entirely. Okay. So I'm just going to show you your task for today. So if you open up your Teams and you look under General, you can do this in a couple different ways. So your team, it's going to be under assignments, but I'm also going to post it on our week 4 lessons. So under assignments, right now I've got it as a draft because I'm going to post it after I post this video, but we can take a peek at it. There's a Word document that you're going to fill in. Make sure you watch the video first, obviously. So part 1, what you're going to do is you're going to find 3 objects in your house that exhibit the following properties. So you can take pictures if you are able to and attach them to this thing so I can kind of see what you've exactly picked. But if you're not able to do that, you can just write me a little description. So 3 items are objects that are opaque. So you need to kind of go check and make sure you understand the difference between opaque, 3 objects that are transparent, and 3 objects that are translucent. I'm going to give you a mark for each of the objects. You just need to write down the object and include a picture in this assignment before you turn it in. Part 2, what would the world look like if the following situations existed on Earth? So this is a fun, kind of silly little question. I've come up with 3 different scenarios related to the content we discussed today. I want to know what you think, how the world would be different if, for example, objects could no longer reflect light. So if objects could no longer reflect light, I can tell you one thing is we definitely wouldn't have any ability to see ourselves in the mirror. But there's lots of other kind of implications and things that would happen if objects were no longer able to reflect light. So I want you to think about kind of what we discussed today. Try and provide as many examples of ways the world would be different that you can think of. So for example, we wouldn't be able to see ourselves in the mirror is a great example. You guys can write that down. So one example there, but try and list as many kind of different things that would be impossible or would be very different if this is the way it was going. If you want, you can draw a picture to illustrate your point if you'd like and kind of include it. But you don't have to. You can just write a little kind of little mini paragraph, about 5 sentences is plenty. And then I'm going to give you a mark out of 4 for it. So if objects could no longer reflect light, if materials could no longer transmit light, and if all wavelengths of visible light, RODBIV, so I'm talking about all of those colors, are either reflected or absorbed and there is no in between, and if all objects transmit light. So you're going to write a little description about each of these questions. That's all the work that you have this week. Next week, we're going to be doing some labs related to reflection and refraction. So I wanted to keep it a little bit more straightforward this week, and I'm also a little late to posting our lesson. So that's the task for this week. If you have any questions, I have extra help tomorrow in the afternoon, which is a little bit soon if you're not quite ready to start this yet. You might not know if you have questions, but you can always ask me questions on Teams. The chat feature is really great. I always am answering chat messages, so don't hesitate to ask. Probably about 10 to 15 of your classmates have already messaged me on the chat to ask me questions, and I absolutely don't mind answering questions on that. Or, of course, you can send me an email, and I have absolutely no problem clarifying a question if you don't understand what you need to do on the assignment, or if you're a little bit confused about some of the content in the PowerPoint. That's a great way to ask me. Okay, so good luck with your assignment. Don't hesitate to reach out, and I'd love to see you tomorrow at Extra Help / Miss Belis does experiments from her kitchen. Okay, thanks. Goodbye.